Okay, so in this lecture I want to talk about conditional probability. And I think this is a somewhat complicated topic, but it's not honestly as complicated as Weisberg's presentation makes out. I mostly like his book. I don't think he does a great job presenting this particular topic. There's a really good method for both thinking about and solving problems with conditional probability, sort of draw a diagram or draw a tree method, that he mentions, but I really don't think he spends enough time on. And I think this is the most intuitive way to think about the problem, okay? So let me give you guys just a word problem, right? You're gonna love this, right? Everybody loves word problems. We all have great associations from high school with word problems, right? Anyway, I stole this one. If you look at the end of the chapter, Weisberg steals a few from me in hacking. I stole this from me in hacking too. He has a really good book on probability and inductive logic. It's honestly a little harder than Weisberg's, and you guys are probably like, oh my god, harder than Weisberg's, this is hard enough, right? It's a little harder than Weisberg's. One reason I didn't give it to you guys, it's also like 50 bucks, I think, which Weisberg's is free, right? And for the most part, I do think Weisberg does a good job presenting. I'm just not crazy about the way he approaches conditional probability. Anyway, let's imagine that you have some bad shocks on your car and you heard, well, my car company has these two suppliers, right? And you want to know who to blame. Suppose Acme supplies 90% of the shocks for a car company and Bolt 10%. We can imagine they usually use Acme, but they run short, so they, are ordering from Bolt, right? 1% of Acme shocks are defective and 5% of Bolt shocks are defective, right? You have a car made by this company, whatever car company we imagine, with bad shocks. What are the chances it's made by Bolt, right? Bolt is way more likely, 5 times as likely, 5% versus 1%, to have bad shocks. Well, what's our probability that your shocks are made by Bolt, given that they're defective shocks, right? And this is very recognizably a problem with conditional probability. What is the probability that your shocks are made by Bolt given they're defective? B will stand for Bolt, D defective. Remember, Weisberg introduces this symbol, probability of B given that D, right? What is the probability that your shocks are made by Bolt given that they're defective? One thing it'll go without saying, I think this is mostly intuitive, this like, B given that D symbol. One thing I'll tell you guys, then this will become really clear as we go through the lecture, this is the one symbol where the order matters. Probability of B given that D is not the same as D given that B, right? The others, order doesn't matter. With this one, order does matter. Also, you guys will notice Weisberg uses this straight line. I'm using a slash. Other books I've looked at use this slash. It's a little confusing because it makes it look like a fraction. It's just easier to type. That's why I'm using it. All right, so let's draw a little diagram. So each of our diagrams, we branch and we say, okay, well, we have bad shocks, right? Well, there's two ways we can get bad shocks, right? We can travel the Acme road, because some of, not as many percentage-wise, but some of Acme shocks are going to be bad. We can travel the Bolt road, right? Insert your own bad joke about the road being bumpy because your shocks are bad, right? Whatever. I can't think of a good joke. I doubt there is a good joke to be made. There is. Tell me, and I will steal it from you as I'm stealing hacking's example here, right? All right. But let's look at these little steps on the way. What Weisberg calls nodes. We don't need to, think that much about that. Look, let's start down the Acme road, right? What are the chances that your shocks are made by Acme? I said 90%, that's, 9 and 10, right? Well, what are the chances if you have Acme shocks that they are defective? Well, that's 1 in 100, right? So what we do is we multiply these previous steps, right? 9/10 times 1/100th, 1/100ths, 9/1000ths, right? Your chances, you know, you know, this is one way we can get bad shocks. 9 times out of 1,000, they will be made by Acme. Well, let's go down the other route, right? What are the chances our shocks are made by Bolt? 1 in 10, right? What are our chances they're defective if they're made by Bolt? 5% or 1 in 20, right? We multiply 1 in 10 by 1 in 20, so 1 time out of 200, we have bad shocks. They're made by Bolt, right? So we add these two together. What are our total odds of defective shocks? What are the total odds, you buy from this car company and your shocks are bad? Well, 9/1000ths on the Acme branch, 1/200ths on the Bolt branch. So we just, look, a little bit of basic math. If we want to add 1/200ths to 9/1000ths, we just multiply until they have the same number at the bottom, right? Multiply by 5. 5/1000ths plus 9/1000ths. 14 out of every 1,000 shocks, 1.4%, not that that matters, will be defective. I don't know a tremendous amount about cars. I don't know if this is a good number or a bad number. It seems kind of bad to me. But if you do know more about cars, you can let me know. Is this a good? I mean, of course, it's bad to get bad shocks, right? But I just don't know what the margin of error usually is. Not that it matters. Well, look, our original problem is, well, you have these defective shocks. What are the odds that they're Bolt, right? Well, one way to think about this is, okay, of this 14 out of 1,000 shocks that are bad, what proportion, what number of those are Bolt, right? Well, we go back, we look 1/200ths, we multiply that to get 1,000. 5 out of 1,000, 5 of this total 14 will be Bolt shocks. If we take 1,000, 14 defective, 5 of those 14 will be Bolt. Now look, you can honestly, you're probably thinking, right, and you can just do this, you're probably thinking, well, I know what the answer is, right? The odds that you have Bolt shocks, given that it's defective, are 5/14. Yes, you're right. Let's go through and do the math, because I do want you guys to see how Weisberg gets the formula he does, right? His way of explaining this I don't think is great, so I do want you to see how and why this formula works. So another way to figure this, to figure out the probability it's Bolt given that it's defective, you divide the probability that it's both Bolt and defective, 5/1000ths, by the overall probability it's defective, right? Do the math down here. 5/1000ths, 5/14/1000ths, you know that old trick from high school math, or maybe it was middle school math. It was elementary school math, I think. At division you just flip, multiply, 5/1000ths by 1,014ths. You end up with 5,000 or 14,000, simplify 5/14ths. This is how you get the formula that Weisberg presents to you, right? So, then we have this conditional probability formula. Probability of A given that B is the probability of A and B divided by the probability of B. And look, what this is getting at is this. You have B, right? And you want to know, well, what percentage, you have B, so what percentage of things are A things? Well, you know, you already have B, so you just kind of divide to kind of cancel it out because you already have B, and now you want to know, since you already have B, well, what percentage of this B circle are A's, right? Here's the thing that might help, right? Look, you know, think of this whole white field as all the things that could happen in this area, right? You know, all the possibilities of this one thing we're talking about. Well, look, once you have, we're thinking about A given that B, we know we're in this B circle. We basically, you know, we divide by B here as a way of representing that just all this stuff outside the B circle we don't even think about, right? Now that we're inside the B circle, well, we ask, well, what percentage of stuff inside the B circle is also A, right? If we're talking about shocks, the B circle is defective shocks. How much of the stuff inside the B circle are these bolt shocks? Let that stand for A, right? What percentage? We see that now that we're inside the B circle, look, there's a lot more. Think about all the white space here, the whole block. We see that, well, a lot more of a percentage of the B circle is taken up by A than is than A takes up the whole white field, right? In this case, because A, makes up a pretty large part of B, B makes A a lot more likely, right? We can think of other possibilities, right? In some cases, B and A might almost completely overlap, right? I don't know what the probability here is, look, I know politics annoys people. We can just go with a politics example, right? What would be the probability that, the next president is a Democrat given that Joe Biden is reelected in 2024, right? There is some tiny, 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 tiny possibility that Biden would decide to switch parties, right? It's never happened with a president. Governors and senators have done it. Tiny, 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 tiny little possibility. This tiny smidge outside of B, right? But super unlikely, if Biden is reelected, you know, then, the odds the next president is a Democrat, A here are huge, right? Because so very little of A is outside of B. And you can imagine cases where B makes A way less likely, right? Again, the whole point of dividing by B is just we overlook the rest of this and we just look, well, before we had B, A was huge. It was pretty likely, right? If we think of the whole white square as our space of possibility, A takes up, I think a little less than half, but close to half, right? But A takes up a tiny part of B, right? In this case, the probability of A given that B is just minuscule, right? Let's say, A could be the probability you do well in my class. B could be, you know, that you've never ever come to any of the Zoom sessions and haven't turned your homework in so far, right? There can be some tiny, tiny little realm of possibilities where that might be true, some tiny percentage of cases where that's true and you still somehow do well in the class. Tell yourself a story. It's gonna be really, really small, right? Much smaller than just the normal odds you would do well in my class. All right, so hopefully that clears that stuff up a bit. I know this is pretty complicated, or seems complicated, and you might look at this formula and be like, well, why in the hell is it that, right? Why in the world do we take A and B and then divide B? I hope, this idea that, well, we're looking at the percentage that this is both true of, or we're just basically looking at the stuff in the B circle. I hope that makes a bit more sense of why the formula is that, why we do that. Now, let's look at another problem in conditional probability. Let's look at a question from our quiz that probably annoyed you. And the whole quiz was supposed to annoy you, right? It's supposed to be like stuff you think one thing and it's not true. It's all supposed to be counterintuitive. The point being, inductive logic can be very tricky, right? So here's the question. Bill is convinced that he has a rare disease, Iriomotic syndrome. Bill doesn't have Iriomotic syndrome, by the way. It doesn't exist. It's from Star Trek. It's the disease that Captain Picard gets in an alternate future where he's very old. And yeah, and anyway, whatever. I like Star Trek. You use your own examples, right? It's from the final episode of Star Trek The Next Generation. One of the best episodes, but be that as it may, that's neither here nor there for our purposes, right? Anyway, let's imagine Iriomotic is a syndrome. We're a real disease, real people, and not just Captain Picard can get, well, and that there's some chance Bill has it. Well, the doctor says, look, people like you usually don't get it, right? It usually strikes women who are older, younger men almost never get it. Literally, there's a 1 in a million chance you have it. So, after a lot of pestering, doctor orders a test. For reasons I'll get to, no responsible doctor would ever do this, but let's just imagine he did, right? And the test comes back positive. What are the chances Bill has this disease? So, correct answer was less than 1%. You guys might be, well, why in the world is that? Let's draw a diagram, right? How do you get to a positive result? Now I oversimplified here. I said 99% accurate. In the real world, we would have to know both the chances that it gives us a false positive and a false negative, whatever. We'll just assume that if you have the disease 100% of the time, it will say you do. Where it goes wrong is 1 time out of 100, if you don't have the disease, it will say that you have it, right? It gives a false positive, never gives false negatives. No test in the real world is going to be like that, but whatever, we just simplify. Never gives false negatives, but 1 time in 100, it gives false positives. The test comes back positive. What are the chances Bill has the disease? Now, some of you might have thought, well, he probably doesn't, right? Because just intuitively, think about it here. One of 2 wildly improbable, unlikely things have happened, right? And which thing is more likely? The thing that has a 1 in a million chance that's happened, or the thing that has a 1 in 100 chance? Obviously, the thing that has a 1 in 100 chance is more likely to have happened than the thing that has a 1 in a million chance, right? Okay. But let's see why we got the answer we did, right? We'll draw a diagram. And trust me, the numbers here get ugly. I had to use a calculator. There's a decent chance I messed them up. Whatever. For reasons I'll get to, the numbers don't matter that much. I just want to make a point, but we'll go through the numbers just, to be precise with this. So look, there's 2 ways to get a positive result on this test. There is, we go up 1 branch, we imagine that Bill doesn't have the disease. In cases like Bill's, that's going to be, in men like him, 999,999 times out of a million, that will be the case. But we can still get to this positive result because 1 time out of 100, the test will get it wrong. So 999,999 times out of 100 million, you will get a false positive. If you ran the test on guys like Bill 100 million times, 999,999 times, you would get a false positive. Well, we go down the other branch, right? Bill has the disease. 1 in a million. Well, we say if you have the disease, it's always accurate, right? That's not going to be the case in the real world, but whatever. So the odds are 1, right? 100%. So one out of all our positives, one time in a million, it will be that Bill has the disease. 999,999 times out of 100 million, he won't. We convert. We add our first number and our second. I'm not going to keep reading this, but we multiply so that they both have the same bottom number. Then we add them and we get this ugly 1,099,000 out of 100 million, right? Well, look, this is our number. If we ran the test 100 million times on guys like Bill, which we can't do, 1,099,000 of those times we would get a positive, right? And remember, after we've done after we've make sure our bottom number is the same as the top, 100 of that 100 million will be legitimate cases of the disease. So I equals Bill has Iriomotic syndrome, P equals he has a positive test for it, probability of I given that P equals I and P, Iriomotic syndrome and positive result, divided by P, probability that Bill has a positive test, right? We run the numbers, 100 out of 100 million cases, will he have it, divided by 1,099,000 out of 100 million, we flip it, it cancels out. So literally his chances of having it are 100 in 1,099,000. Which, if you want to do the math, is a bit less than 0.01%. So, don't worry about the numbers there, right? There is a decent chance I've messed them up, and some jerk on YouTube is going to tell me I'm a moron for messing my math up. People live on YouTube to do that. It's a sad life when that is the highlight of your day, is to tell someone on YouTube that they have messed up in trying to explain something. I've run into these people, and I kind of pity them. Even though in the moment when they make the comment, I kind of want to punch them in the face as well. But whatever. Those are not inconsistent. Well, look, what's the point of all this, right? What's the point of me going through these elaborate examples? What's the point of even talking about conditional probability, given that it's kind of confusing? We have all these fractions which are a pain in the ass to deal with, right? I mean, fractions aren't hard math, but they're just a pain in the ass, especially when you're dividing one fraction by another, right? I say this is a pain in the ass because this lecture was, and I will say it again, hopefully you won't mind my language, it was a pain in the ass to do and to work with these fractions. What then is the point of all of this? The point of all of this is that you can't know the probability of A given that B unless you know both the probability of A and B and the probability of B. You need to know, what the probability, in my medical test case, you need to know the probability of both a positive test and him having the disease. You have to take a lot of stuff into account. You can't just think of, in Bill's case, you can't think of how accurate the test is on its own. You also have to think of, well, how likely is it he actually has this disease? In the shock example, you might get misled because you think, well, 5 times the number of shocks made by Bolt are defective versus Acme, but you have to look at the percentage of shocks made by both Acme and Bolt, right? You have to take all that into account to know what the conditional probability is. We'll talk more about this stuff in a few lectures, but this is important, right? This gets into a very deep and persistent fallacy, which I'll talk a lot more about in a few lectures. The fallacy I'm going to mention today, and the one we will talk a lot more about in a couple lectures, are I think, is one of the most important things. Learning about this fallacy is one of the most important things I think you can learn from this course. The whole reason I do inductive logic is to talk about this fallacy that I'm going to mention today and the gambler's fallacy that we talked about last week. Anyway, you have to take all this stuff into account. And now look, my toy examples, I say they're toy examples because they're oversimplified, like a kid's toy, are much simpler than the real world. My examples are already, like I said, they're already enough of a pain in the neck to do the math. They simplify, right? But stuff like what happens in these examples does happen in the real world, right? And what this means is that you can't, to take just an example from today, you can't interpret medical test results in a vacuum. You have to know the odds given a person like this. What are the odds of both a positive test result and them actually having the disease, right? In the real world, what a medical test result means will be relative to age, gender, health, etc. A test will mean something very different for a 20-year-old who's very unlikely to have the disease than it will for an 80-year-old who is already quite likely to have it. Give you guys an example from my own life. My wife was pregnant. We had genetic testing, right? And I asked the genetic testing counselor, I asked her, I'm like, okay, what are the odds of a false negative? What are the odds that, this says that the babies have a genetic problem when they don't? And what are the odds, what are the odds of a false negative? What's the odds that they have a problem and it misses it? And what are the odds of a false positive, right? It says they have a problem and they don't, right? And she says, the odds of a false negative are low anyway. The odds of a false positive for people of you and your wife's age are very low, right? She called us old, right? And what this means is, as you get older, you're more likely to have genetic problems. I mean, thank God we didn't. But you take that into account. A positive result for somebody much younger than us, because they're unlikely to have those problems in the first place, there's a better chance that it would be a false positive. For people of our age where these things become much more likely, a positive result is much more worrying, much more damning, right? Because you have to take this stuff into account, the background. Now, what this means in the real world, to know what the probability of A given that B is, you have to know the probability of A and B. Well, and the probability of B, in the real world, you're almost always going to have to know what the probability of A before you had the test or had bad shocks or whatever is. You can see this on these trees, right? If you didn't know what percentage of shocks were made by Acme and what percentage were made by Bolt, you would never be able to figure out the proportions here, right? You would never be able to figure out, well, what the total number of defective shocks are, and also what are the odds of defective and made by Bolt, right? This bottom branch. The same goes with my elaborate story about Bill, right? You need to know the chances that someone like him will have the disease before you ever do the test, before you can figure out what the test means. So, and the failure to know what A is, or worse, ignoring that, leads to all kinds of stupid mistakes. Failing to do that even has its own name. Philosophers call it the base rate fallacy. We'll talk more about what the base rate fallacy is in a couple weeks, or in a week, but hopefully you guys can start to see how this pops up, why it's a fallacy.